Okay, good evening, guys. So, as promised, I'm supposed to actually give you some tutorial questions on partial derivatives, where I'll be solving those questions real time, and you guys can actually pause the video and solve the question and later follow along my solutions. So, the question actually, I got it from our textbook, Modern Engineering Mathematics by, I think the author's name was Glyn or something. Later I'll check and let you know. But I have already given the book title to you before, and this will be the question actually from the book. So we have a function here where, all right, just give me a minute, okay? Where we have a function here of f, okay, respect to x, y, and z, and the function is x square, okay, so x square y plus 3xy is 3y x z, okay, minus 2z cube 2z cube x squared y. So this is the partial derivative here, okay? And we are asked to find what is fx, what is fy, and what is fz. So I'll give you this moment to pause yourself and actually try to figure out what is fx, what is fy, and what is fz. Okay, so after you've already managed to pause the video and try to figure it out, let's work on the problem together. Actually, it's a very straightforward problem. So recall that fx, okay, is just simply del f over del x, right? So that means when you actually solve this partial derivative, let me just highlight in different color green, yes? So if you solve this, by the way, right, it's actually pretty straightforward. It's just simply 2xy, right, plus 3yz, all right, minus, so this is like 2 here, and this is a 2 power of 2, so you multiply together become 4x z cube y, okay? So that is your partial derivative for with respect to x, del f del x. Now we're talking about the case for y, okay, which I'll write here as fy. Otherwise, we can write it as del f over del y. All right, it's very straightforward. We differentiate y, everything else is a constant, yeah? So you get here x squared plus 3xz, okay, minus 2x squared z cubed. Okay, y is being differentiated out. So that is your partial derivative with respect to y. Now for fz, all right, okay, fz, I'm going to write right here. It is just simply del f over del z, okay? And actually, when we are differentiating respect to z, this, right, x squared y would not be considered. It's just a constant, so it's just gonna be like, you know, 0 in this case, so we're gonna ignore it. Then here we'll just take it as 3yx minus, so become 2 times 3 becomes 6 z squared, okay, x squared y. All right, so this would be the case for del f del z, all right, the partial derivative for this question right here. So we've actually managed to solve for this particular question right here. Let me just call it white. So yeah, so that is your fx, that's your fy, and that is your fz. So let's do another question. Actually, I'll erase this one right here, and we'll do another question actually to solve this problem. Okay, good. So now we are gonna solve another question also from the textbook. And if I'm not mistaken, the function actually in terms of x, y, and z for this one, yeah, it's just fx, y, z. It's gonna be e to the power of 2z cos xy. Okay, right? So that's your function. And also similarly, we're asked to find what is fx, what is fy, and what is fz. Okay, so I'll give you a minute to pause and try to figure out how do you get for fx, how do you get for fy, and how do you get for fz. Okay, so now you come back and you want to see how do you solve it. So fx, remember, is just the differentiation, so it's just del f over del x, right? So when we are differentiating respect to x, do bear in mind that this is actually a constant. The exponential term e to the power of 2z is just a constant, okay? It's not gonna affect in terms of x. The one that we're really interested in is the cos x y, right? So x is our focus and y also, let me just mark in a different color, is the constant, okay? Is the constant, or let C. So therefore, our interest should only be concerned about the constant. I mean about the cost, the cosine term, not the constant, my bad. Right, so we have e to the power of 2z. Okay, we leave it as it is, we don't touch it. And we have cos xy, cosine xy, right? And if you guys remember your chain rule, we also differentiate the inside. Remember, we also differentiate the inside part. So therefore, I'm going to switch it back to yellow. We're going to have y, right? So I'm going to simplify this. It's just simply y e to the power of 2z, right? Cosine xy. Okay? So that is your uh that's your um effects. Now we're not dealing with Fy, all right? It's gonna be del F over del Y, right? And same thing goes for X also, as I mentioned earlier. Let me just take and erase it for a minute here. Let me just erase this. Okay, okay. So we're only interested in the cosine part, right? So therefore, give me a minute, yeah. Okay. Therefore, this x is our constant, and our y is the focus, the one that we wanted to differentiate of. And e to the power of 2z is also a constant. We can treat it like a constant, so there is nothing to worry about. Therefore, I'm going to leave it as e to the power of 2z, all right? Again, times with the cosine xy. I probably put a dot here actually so that you guys can understand multiplication. My apologies. Times, okay. As I said before, x is a constant, y is the one we're interested in. So don't forget your chain rule. We just differentiate it, we get x. So we'll just write it as x e to the power of 2z cos xy. All right. So that is our fy. Very easy, right? It's not actually harder than we think. Then the last one is our fz, right? So fz, when we do the differentiation del f del z, okay, now what we're interested in is we're only interested in the exponential function, right? Let me just erase these parts right here. Okay, so we're only interested in the exponential part. We're not interested in the cosine x, right? We're really interested in this one, by the way. So if we differentiate correctly, we know very well that when you differentiate an exponential function, right? We obviously will have e to the power of 2z, just like normal. But don't forget to do your chain rule. Let me just put a dot here. So we differentiate the inner term as well. So therefore it becomes 2, right? With respect to z. And the cosine xy is just a constant that we just leave it as it is. Okay, and rearranging the equation, we got 2e to the power of 2z, okay, cosine xy. All right. So as you can see, this is we've managed to determine for fx, fy, and fz. Okay, it's pretty straightforward. It's not actually as hard as we think. And now let's proceed to another type of question from the textbook as well. So I'm going to have to erase this. Let me just erase this here real quick. Wow, okay, erase. Let me make this brush erase a little bigger. Okay. Okay, great. So let me write the next question. So the next type of question actually I've got here, it's more of like a show kind of question. Let me change that to yellow. Whoops. It's more of like a show kind of question, all right? It's more like a show. Like we want to show how we get from A to B, for instance. Is that kind of question, all right? So let me let me write the question down. So that all right? So we want to show that f, all right, when we write the multivariable function f, x, y, z, okay, which is equivalent to, oh wow, it's a very long function right here. It's not that long, but yeah, just x squared plus y squared plus z squared, all right, to the power of negative half, all right? So remember negative half, also we can write it like this, is just simply 1 over the square root. Remember that the power of half always refers to the square root. So it's just x squared plus y squared plus z squared, right? Show that this function satisfies this rule. So it has to satisfy something. Okay, normally when I ask you to show something, you have to always make sure that it satisfies or it fulfills a criteria. In this case, it is x, sorry, my bad, x, fx plus y, fy, right? Plus z, fz, okay, equals to negative f, x, y, z. Okay, so we have to actually show that our multivariable function right here, fx, y, z, okay, fulfills this thing. All right, we have to make sure that it fulfills this thing. So I'm gonna give you some time to pause into this formula and try to figure out how can we actually show that this is this. Then I'm gonna actually delve into the answer straight away. Okay, so I assume that you've paused and gave your best shot in how to solve this problem, and let's go and discuss the problem. So the first and the foremost thing, step one. What's this? What's step one? So step one, right? To approach this kind of problem, obviously you want to find what? You want to find fx, fy, and fz. Okay, you want to find these three first, right? And as we know it, fx is what? Fx is del f over del x. We've already known that earlier. Okay, so when we differentiate this function right here with respect to fx, right? I mean with respect to x, sorry, my bad. So the rest of the terms, the y and the z, okay, let me just highlight a different color, yes. The y square and the z square, treat it as a constant, okay? Treat it like just some any other constant. Don't forget that. So let me go back to here, okay? So we're just going to, so we're going to differentiate it, right? Del f del x. So first of all, bring the half here. So it's half, right? Negative half, we bring it here. Becomes x square plus y square plus z square, okay, to the power of So it's negative half minus 1. So it should be negative 3 over 2. Okay. And then remember to don't forget your chain rule. So you have to differentiate the x squared inside it. It'll become 2x. Okay. And if I were to simplify this, it's just simply negative x. Okay. X squared plus y squared plus z squared to the power of negative 3 over 2. And I do apologize for the fireworks that was actually blasting outside my room. I do not know what people are celebrating at this time of the night. It's already midnight, by the way. So, yeah, I don't know what's happening out there. Moving on, we have Fy. Okay. So, Fy actually is del F over del Y, right? So, we're also going to do the same thing. Essentially, it's the same stuff actually because when we are differentiating in terms of Y, right? Then the x and the z becomes constants, right? And the y is not the constant anymore. So let's just move on to it. It's almost the same form, so that's a relief actually. You don't have to panic so much about it. All right, so it's just x squared plus y squared plus z squared. All right, to the power of negative half times 2y. Okay, so essentially it is just negative y. Okay, then we have here x squared plus y squared plus z squared to the power of negative 3 over 2. Oh yeah, by the way, I forgot, my apologies. This is supposed to be a negative 3 over 2, not a 1 over 2, by the way, right? So let me go back to and correct it. So it's negative 3 over 2. Okay. And then I see we don't seem to have much space actually. But obviously when you also do your FZ, right? The pattern is the same actually, it's just del F over del Z, okay? And if you were to also do it, you would eventually find out it's just, my God, sorry. It's just negative Z, all right, to the power of multiply of x squared plus y squared plus z squared to the power of negative 3 over 2, okay? So I've already managed to find your fx, your fy, and of course your fz. It's pretty simple. Now we need to plug it into this equation. We need to actually show that it satisfies this condition. That is step 2, by the way. Okay, we need to show that this satisfies this equation. So I'm going to erase all this, by the way. I'm going to have to erase all of this. We are going to erase all of this. All right. Okay, and I'm going to have some space to write for step 2. Sorry, make that yellow. Okay, so we have here step 2, okay, where it's just simply plug fx, fy, and fz into this equation basically. Okay, so we want to plug it to here. Okay, so I'm gonna have to also erase this part as well, just to show you how it's done. Okay, cool. Right, so we have here x times del fx. If I recall correctly, it was just negative x bracket x square plus y square plus z square, okay, to the power of negative 3 over 2, all right, plus y, the same thing also, so negative y times y square, sorry, not y square, x square plus y square plus z square, all right, to the power of negative 3 over 2. and also we plus it with z. I'm just write nicely for you so that you guys could see clearly. Z, all right, times with negative z, okay, x square plus y square plus z square, okay, over negative 3 over 2. All right. So what happens here is that we can see that the x with times with negative x, y we can multiply negative y, whereas z we multiply negative z, right? So we end up getting negative x squared, okay? The negative sign doesn't go away, by the way, minus y squared minus z squared, okay? And of course, we also have the common factor. Okay, what I'm trying to do is actually I'm trying to simplify here. So you can all see that all of them have this common factor, right? X squared plus y squared plus z squared to the power of negative 3 over 2. So I'm going to take that out. That's why I'm actually sort of breaking it down, making it simpler for everyone. So it just becomes x squared plus y squared plus z squared to the power of negative 3 over 2. Okay. So what happens is I'm going to take out the negative sign here actually. I'm going to sort of take out these negative signs, by the way. So it's going to be quite simple, quite simply. It's going to be negative x squared plus y squared plus z squared. Okay? Multiply x squared plus y squared plus z squared to the power of negative 3 over 2. So what we can see right here, actually, this becomes a very simple problem. We're just multiplying this. This one obviously is a power of 1, and this is a power of negative 3 over 2. Okay? So, of course, 1 plus negative 3 over 2 is how much? I think we already know that 1 minus 3 over 2, 3 over 2 is just simply negative half, right? So I'm gonna have to erase this, by the way, this part here where it's getting complicated. Okay, and erase this. Yep, because I don't really have space. By the way, space is quite limited. Okay, erase this, by the way. So we're done with our step 2. Okay, and we can see that if I we've let me make that yellow. Sorry, we can see that we end up getting uh negative x square plus y square plus z square, okay, to the power of negative half. And they wanted us to show, and this part, by the way, sorry, this part, by the way, is our f, x, y, z. Okay, so we've already managed to prove that by finding the partial derivatives, okay, finding the partial derivatives, let me just, okay, we find the partial derivative of fx, fy, and fz, right, from this particular equation, and then we multiply with x, y, and z respectively. We're able to prove that we got the negative of this multivariable function right here. So it's already proven. All right, so it's actually a pretty straightforward question, but I just wanted to show you guys how we can also prove such functions. All right, on to the next question. Let me just erase this, by the way, so we have another question also as well. All right. Just a reminder that whatever questions I do or like show on the board, you guys should at least pause and try to attempt it yourselves before you resume the video and watch me working out the solution actually. That way it will help you guys to, how do I say it? To understand the question, to understand the thought process behind it, and if you are stuck or you're having any troubles, it'll actually be easier for you. Okay. So now I'm going to go to one more show question for the day before I end this video. So we have another show question, right? So, whoops, I'm using white color for that purpose. Whoops, right, yellow. Right, so show that, okay, we have a multivariable function again, f, x, y, z. Oh, why is it not typing? Why is it not writing? Okay, z is equivalent to x plus x minus y, all right, over y minus z. Okay, if we have a multivariable function like that, we want to show that it satisfies, okay, this relationship that fx plus fy plus fz is equivalent to 1. We want to show how it satisfies the relationship. All right. So again, similar like last time, I give you guys uh some time to solve this problem. Just pause on the video and try to work this out, and later I'll work on the solution. Okay, so I've assumed that you guys already have given your attempt and tried to solve for this problem. So let's work on the solution together, right? So again, the first step, what's the first step? Remember, we obviously try to find fx, fy, and fz. We try to find these three. Okay, so for fx, which is obviously, remember I told you before, it's del f, yeah, my writing looks so bad, del f over del x, right? So in this case, we know that our x, there's two components. There is the normal one, right? Just a simple linear function, and there's also a fractional one, but the x is only on the top, the numerator side, not on the denominator. So this one we can treat it as a constant. This one we can treat it as a constant, by the way. Right, constant. Okay. All right. So moving on, right? So this will obviously become 1, and this one is just simply x minus y. Okay. No, hold up. Sorry, it's not right. So this one we write is 1 over y minus z. Okay, because it's just a simple constant times with 1. Okay. Since when we differentiate x minus y, when we differentiate x minus y, by the way, yes, it's actually the same as saying x minus 1. So of course, when you differentiate with x minus 1, you end up getting 1. Because this one is a constant, you can forget about it, right? That's why I just multiply by 1. And if I were to simplify it, it would be, yeah, it just become 1 plus 1 over y minus z. Okay, pretty straightforward. Now, when it comes to fy, right, where we know it's just simply simply del f over del y. Okay, so we obviously have y in two terms. Let me just erase this to make it clear. So, okay, we have y in two terms, right? Okay, we have the numerator, and we also have y in the denominator, right? And this one we can treat it just like a constant. This is like just a constant anyway, so nothing to worry about here. So in this case, we have to do something called the um, quotient rule. Remember the quotient rule, that if you have a function, if you have like a y in the numerator and the denominator, so we have to definitely do the quotient rule actually. So to do the quotient rule, right, it's just simply v du dy minus u dv dy okay, over v square. So quite simply, it is just v is obviously your denominator, right? So we take this as our v, and we take this as our u, the numerator part. So please don't be confused. So it is just simply y minus z, okay? Du dy is just -1 minus u, the numerator part is just x minus y, okay? Dv dy is just simply 1, okay? Over v square. V square is just y minus z squared, okay? So if I were to simplify this, it's just simply y minus z. So it's just negative y minus z minus x plus y over y minus z squared. And of course, if you simplify this further, okay, let me just cancel out these two so this one can get cancelled out. And we'll end up having uh z minus x over y minus z squared. Okay, so that is your fy. Now, to find fz, all right, it's almost the same as fy actually. It's in fact the same procedure because just like for the case of y, our x is a constant which can obviously differentiate. Oh, there's only one difference. I'm so sorry. The z is only lying on the denominator. There's nothing on the numerator, by the way, for z. All right, so let me just erase this. By the way, let me just make it more clear, by the way, so you all understand and follow. So our z is only lying at the denominator. Okay, so we have to worry about the denominator part. So it's like, for example, it's just you treat it like 1 over 1 minus z. Okay, so we have to differentiate that actually. Or we can make it more simpler, just like 1 minus z to the power of -1, right? Very easy differentiate. Okay, so let's just do it right now. So fz, okay, hopefully we can finish it. Fz is just obviously del f over del z, okay? It's just, we have a constant, obviously it's x minus y, so that's a constant, times negative y minus z. All right, because we're moving the denominator on the top, so the power will become -2, and then times with -1, because we're differentiating the inside using the chain rule. So as we're doing it, what happens is that the negative here, right, the negative, I'm going to highlight in green, by the way, this negative and this negative will obviously become positive. So therefore, we would actually end up having x minus y, right, over y minus z squared. Okay, so we've managed to also got our del f del z. It means our fz. Now, the next step, as I've told before, is to obviously show this relationship. When we plus fx plus fy plus fz, we're able to get 1. That's the most important thing, actually. Right? So let me just erase the stuff here because we are having so much stuff here, we cannot really do anything. Okay, let me rewrite the equation first. So fx, as we know before, it's 1 plus 1 over y minus z. You can see our step 2, by the way. Yeah, remember with our step 2, where we just have to plug it in, right? Just plug in these values. So 1 plus 1 minus yz plus negative x minus z over y minus z squared. Okay, and last one is plus, sorry, my plus not writing very nicely, by the way, plus x minus y over y minus z squared. Okay, I just want to write it down so I can actually erase off the other part before I forget. Yeah, so that's why I wanted to write it down. So just 1 plus 1 minus that. Okay, okay. You can erase this part also as well. All right. So erase this part properly. Okay, clean now. Okay, perfect. So now we try to simplify this problem. So we have here 1 plus 1 over y minus z. Okay. And then we have these two terms, obviously, which are having the same denominator. So that should be quite easy to solve. So it should be negative x minus z plus x minus y over y minus z squared. Okay. And as we can see, this will eventually cancel out. Oops. So what happens is that we end up getting 1 plus 1 over y minus z plus negative z minus negative y over y minus z squared. Okay. So we still need to solve it clearly. So it's definitely, we have to make sure they have the same denominator. So it's supposed to be y minus, you see different color. We need to make sure that it's supposed to be y minus z squared. So this one and these terms, we definitely need to change the denominator. So it become y minus z squared, okay, plus y minus z, okay, and we would obviously have here minus, sorry, plus negative y minus z, okay, over y minus z squared. Wow. So how do we do this? Of course, we have to factorize. We have to open everything. So it becomes y squared minus 2yz, okay, plus z squared plus y minus z minus y minus z over y minus z squared. Okay. So we can obviously cancel out the common terms. So we can definitely cancel out y right here. Okay. And yeah, let's see what we have here. We have here negative 2z. So we would have here, okay, we'd have here y squared minus 2yz plus z squared minus 2z, okay, over this entire thing, right? It's just y minus z squared, okay. So now we need to prove that this is actually equivalent to 1s, right? We need to make sure that uh, it satisfies this equation, right? Okay, how do we do this? Because y squared minus 2yz plus z squared minus 2z. Mm, how are you gonna solve this equation? Hold on. Squared minus 2yz, z squared minus z squared. Okay. So we can see here actually, now we probably have to erase this by the way, maybe we have to erase some space or something. because we're really lacking of space. I'm gonna have to do it here a little bit. I'm so sorry. So it's gonna become y squared, right? Um, hmm. Is it right? Z minus 2y minus 2, not 2, that, sorry. Minus 2, supposedly. Mm, hmm. No, it doesn't seem right. Hold up. Let me see here first. I don't think it's right. Hmm. Let's just check the original equation because I have a feeling that something's quite wrong here, by the way. Let me just try to see first. So it's obviously 1 plus 1 minus 1 minus z. Okay, and then for fy, when we try to do this, we of course get rid of the x, right? We got minus y, and then we got here minus z, right? And we have here obviously y minus z squared. Okay. Um, that seems to be a problem actually. I think we might have made a mistake here in these terms. Otherwise, we should by right we should be getting one actually. I think this should be canceling out. What I'm trying to say is that this should actually by right be canceling out with this one, and then our answer should be one, because that's what they're asking us to prove. That's why I'm suspecting maybe we did something wrong with fy here actually. Our fy might be wrong. That's why we're not able to cancel it out properly. So let me just rearrange this, by the way. I know it's going to take a bit of time. So let me just rearrange this and let me just verify for fy. Otherwise, it shouldn't be this hard actually. Sometimes we can make some algebraic mistakes also, and because of these algebraic mistakes, this can actually also affect us. So it's always good to counter check before you solve such problems. So let me go back again for fy. So let me just double check for fy. Fy, it's obviously like we said before, we have to use the quotient rule, right? U and we use v, right? The whole thing. So it should be I'm marking green. It should be v du dy minus u dv dy over v squared, right? Yeah, it should be like this. We'll check. So v is clearly y minus z. Du dy is -1, right? So it's -1. Okay. That's where a mistake is. Okay, minus u dv dy is just simply 1. Ah, and v squared is just simply y minus z squared. Okay, that's where a mistake is actually. So you got negative y plus z, okay, minus x minus y. Sorry, plus y, my bad. Over y minus z squared. Okay, so you can see my mistake actually was a sign mistake. I forgot to pay attention to the correct sign. So obviously we know that this cancels out, right? And therefore we should be getting z minus x over y minus z squared. So you see, My mistake actually was that. So let me just erase this real quick. Okay, what's a huge brush size? So I'm gonna erase that real quick. Yes, sir. Okay. Oh my God. Okay. So it's z minus x. Okay. So now everything falls in place supposedly. Now it shouldn't be a problem. So this is your FYS. So don't forget to correct your mistake. Right? That's what I did actually. That's why I realized it didn't really work out. Otherwise, it should have worked out a long time ago. Okay. All right. So now we solve the problem. Right? So we'd have here 1 plus 1 over y minus z. Okay. Plus z minus x plus x minus y over y minus z squared. Okay, so we should have here 1 plus 1 over y minus z plus, so obviously this cancels out. Okay, z minus y over y minus z squared. Okay, and 1 plus 1 over y minus z plus, if you rearrange the equation and take out the negative sign, so negative y, right, minus z. Okay, and we know that y minus z squared is just simply y minus z times y minus z. Okay, therefore it's very simple. You can just factorize it and you get here 1. So you get here 1 plus 1 over y minus z minus 1 over y minus z. Okay, easily cancelled. And tada, magic. You get your answer 1. Just make sure it's white, yeah. Okay. So yes, hooray, we managed to actually prove that we satisfy this equation right here. Now, of course, we could have reached much faster if I didn't made a mistake in FY. I actually made a very careless arithmetic mistake actually. It's supposed to be z minus x, yeah, out of y minus z squared, not what I did earlier. So it's a very simple problem actually. Right, make sure it's white color. But yes, so it's very crucial to check your algebraic or arithmetic mistakes before we solve such problems. And I know this problem is quite straightforward. It's pretty easy problems. And that's why I advise you guys to actually give it a try. Try to pause the video when I write the questions and try to attempt to solve the problem. Then later when you resume the video, you can actually follow through the answers. I'll be making more videos like this actually for other exercises and partial derivatives soon. So yeah, stay tuned and yeah, have a very good night. So yeah, I wish to see you guys soon someday. So yeah, good night. Right. All right. And take care.